Okay, and it is now my pleasure to introduce Dominique Hulin. I hope I got it right. Thank you. And she is also from Paris, like our first speaker. And this is the title of her talk, Harmonic Maps in Negative Curvature.
So first of all, I would like to thank the organizers for having invited me to this beautiful conference. And yes, I will speak about harmonic maps in negative curvature, and the theorems I will be speaking of at the end of my lecture are a joint work with Yves Benoit. So first of all, of course, I will begin by recalling what a harmonic map is. Okay. So given two Riemannian manifolds X and Y, we say that a smooth map between these manifolds is harmonic if it is a critical point for the energy functional. And going to the Euler-Lagrange equation for this functional, we see that the harmonic map is the map is harmonic if and only if it is a solution of nice nonlinear but elliptic PDE, namely H is harmonic if the trace of its second convariant derivative vanishes. Okay, so now you certainly want to have some examples of harmonic maps. I will give only very simple examples. First of all, examples where either the source or the target manifold are the real line. So when the target manifold is a real line, then a harmonic map is simply a harmonic function. Yeah, it's two. Yeah, thank you. Now, when the source manifold is a real line, then a harmonic map is simply a geodesic with constant speed. You can elaborate slightly on this last example. And an isometric immersion from a manifold to another is harmonic when the image is a minimal submanifold. So now, one of the central questions in the theory of harmonic maps is the following. You are given two Riemannian manifolds and a certain family of maps between these two manifolds. And the question is whether this family does admit a harmonic representative. So this question, this problem, was in particular tackled by Ilse and Sampson in the early 60s. And they proved that when X and Y are both compact manifolds, the latter having non-positive curvature, then any smooth map between these manifolds is homotopic to a harmonic map. So now I would like to state a special case of this result. Then I focus on the case where both manifolds are the same compact surface, but equipped with two different hyperbolic metrics. And then, for example, the identity map between this surface is homotopic to a unique harmonic map. Uniqueness here comes from the fact that now I suppose negative curvature, strictly negative curvature. So, well, this result is beautiful because, well, you know, when you have, or you don't know, I don't know, when you have a harmonic map between surfaces, then there is an object which is associated to this harmonic map, which is called the Hopf differential, which is a holomorphic quadratic differential on the source surface. And this result gives you a with some work afterwards, gives you a parametrization of the Teichmuller space on S by the space of holomorphic quadratic differential. But I will not dwell on this. Rather, I would like to ask whether you can relax in this last statement the co-compactness assumption. And actually, this question was raised in the 80s by Rick Schoen in the form of the following conjecture. So the conjecture states as follows: any quasi-isometric map from the hyperbolic plane to itself is within bounded distance from a unique harmonic map. Here, bounded distance means uniform distance. We require that the supremum of the distances of the images of any point on X by either the quasi-isometric map F and the harmonic map you're looking for, H, the supremum must be bounded. So, Pierre, in the last talk, already defined you what quasi-isometric map is. I will recall you later on the precise definition, but let's recall for the moment that a map is quasi-isometric if it's by Lipschitz at large scale. And I think you have had enough motivations during the last hour for studying quasi-isometric maps. Well, Schoen conjecture was later on generalized by Lian Wang to any quasi-isometric map from a Riemannian symmetric space with rank 1, non-compact type, to itself. So they conjectured existence, but they proved a uniqueness in this setting. Now, these conjectures attracted a lot of attention. And I cannot quote every people involved in it. And I will jump to a recent result by Vladimir Markovich, who finally settled the initial Schoen conjecture, that is for maps from H2 to H2. And in a subsequent joint paper with Marcus Lem, extended this result to maps from the hyperbolic space of any dimension to itself. I cannot also but quote a much earlier result by Pierre Tansu, who proved the same result for hyperbolic spaces over the quaternions or the octonions, with a specificity that in this case, the harmonic map you end up with is isometry. So a special case of harmonic map, very special case. So now let's turn to our first result. It's the same statement, only we change the manifolds we are allowed to work with. So I'm given now X and Y, two pinched Hadamard manifold. And same result again, any quasi-isometric map from X to Y is within bounded distance from a unique harmonic map. So, of course, I need to explain you what are pinched Hadamard manifolds. So, they are Hadamard manifolds or Riemannian manifolds, which are complete and simply connected. If you are speaking about only Hadamard manifold, you only require the curvature to be non-positive. Here I am speaking about pinched Hadamard manifold. This means that not only the curvature is non-positive, but it's bounded both below and above by two negative constants, so it is pinched. Okay? And you have a whole list of examples. First one you would think of, the non-compact symmetric spaces with rank 1, of course. And a lot of non-homogeneous examples, as you can imagine. So now, let's get back to quasi-isometric maps. So this is a definition you already saw during Pierre's lecture. So a map between two metric spaces is said to be quasi-isometric whenever the distance of the images of 2 points is bounded both above and below by an affine map of the distance of these 2 points. And if we want our theorem to be slightly interesting, we need to have a lot of quasi-isometric maps between pinched Hadamard manifolds. So I will give you some examples. First of all, I would say a list of examples that would look theoretical, not hands-on. A theorem by Bank and Schramm, the same Bank and Schramm that Pierre told you about in the last lecture, asserts that if X is a pinched Hadamard manifold, then you can find a quasi-isometric map from X to an hyperbolic space of sufficiently high dimension. Okay, so big series of examples. And now an example that I like much because it is a hands-on example obtained by bending, so-called bending. So I will draw a picture to explain you how to build a quasi-isometric map from H2 to H3, but of course the constructions goes in higher dimensions. No change. Okay, so here, this is supposed to be the ball, the round ball, the ball model for the hyperbolic space H3, and with a totally geodesic H2 inside. What I have drawn in this totally geodesic H2 is a family of mutually disjoint geodesics. Okay? The red one is my preferred one because it passes through the origin in the disk model, so it will be helpful for my drawing. And what I do is each time I meet a geodesic, I bend the plane by a certain angle. So I did draw what I have in mind just when I crossed my preferred geodesic. But you imagine that each time you cross one of the geodesics on the picture, you bend by a certain angle. Okay? And then you repeat the procedure each time you meet one of the geodesics of your family. And playing a little with hyperbolic geometry, you see that you end up, by doing this construction or your perhaps countably family of mutually distant geodesics, you end up with a quasi-isometric map from H2 to H3, provided that the angles you bend with are not too large. You cannot flip, of course. Oops. It's not allowed. The angles are not too large, and the geodesics are not too close from each other. So in the silly picture on the right, I tried to evoke you what happens after this series of bending, possibly infinity series of bending, and what happened at the boundary. And we end up with a quasi-isometric map which has a boundary value. We'll see that in a moment. And this boundary value is what we call a quasi-circle. Let's go to that. So let's get back to general Hadamard manifold, X and Y. And see the fact that any quasi-isometric map from X to Y continuously extends to their visual boundaries, to their visual compactifications, so that there is a boundary map from the visual boundary of X to the visual boundary of Y. What are the visual boundaries? Oops. Look. It's a horrible drawing. I'm sorry, but I tried not to change my hand, and I'm right-handed, so I blew it. So it's an equivalence class of geodesic rays, and you identify two geodesic rays whenever they stay within bounded distance from each other. Okay? So, for example, in the disk model, the visual boundary of the hyperbolic space is just a sphere. It looks to be at finite distance, but it's boundary at infinity. Okay. And now, moreover, two quasi-isometric maps do have the same boundary value if and only if they are within bounded distance from each other. So this fact allows me to rephrase our theorem in the following way. I mean, I begin with a quasi-asymmetric map from X to Y, and I am looking for, and I find actually, a harmonic map which is within bounded distance from F. This harmonic map is still quasi-isometric, and it has the same boundary value as F. So what I'm doing in this theorem actually is to solve a Dirichlet problem at infinity. Okay, I find a harmonic map with boundary value which is quasi-isometric and which boundary value at infinity I prescribed. So a special instance of my theorem, I will rephrase it, is that an quasi-circle is the boundary map of a unique harmonic map. So what is a quasi-circle? Well, first of all, it's a map from the circle S1 to the two-sphere S2. And there are literally dozens of equivalent definitions with so many different flavors of quasi-circles. But the one I will use today, because it's so convenient, is that a quasi-circle is actually the boundary value of a map, quasi-isometric map from H2 to H3. So the map goes from H2 to H3, it's quasi-isometric. Its boundary value starts from the boundary of S2, that's S1, to the boundary, well, it's not B2. Oh, sure. I will write it down. Sorry. So when F is quasi-isometric from H2 to H3, its boundary value is a map from S1 to S2, which is a quasi-circle. And so a special instance of our theorem is that any quasi-circle is a boundary map of a unique harmonic map from H2 to H3. Okay? So this is only our theorem back. Because now what I want to do is wonder whether we can relax the hypothesis in our theorem. So, for example, we can try and relax the pinching hypothesis and allow, for example, for some zero curvature. So in this case, this may work and this may not work. An instance where this works is a theorem by Kleiner and Leib, who states that when X is an irreducible symmetric space with rank at least 2, any quasi-isometric map from X to X is within bounded distance from an isometry, which is again a special case of a harmonic map. So this is partly yes, but partly no, with this simple counterexample. So here X is what we want to be, perhaps a symmetric space with negative curvature, I don't mind. And you consider the map that goes from X to the product of X times the real line. That's the first factor is the identity map, and the second factor is the distance to a fixed point. Though there cannot exist a harmonic map within bounded uniform distance of F, because the target manifold being a product, a harmonic map would have two components which should be harmonic maps. So the first one would be the identity, okay, no problem with that. But the second one should be a harmonic function within bounded distance from this function, which is proper and bounded. This would contradict the maximum principle. Okay. So another way you could think of relaxing the hypothesis in our theorem is relax the quasi-isometry hypothesis. Keep flip sheets, okay, or rough flip sheets, and forget about the separation condition. Okay? Well, this will not work. And this is a very simple example. So let's consider, now I work in the half-plane model for the hyperbolic plane. Let's consider the map, which reads as follows. You can easily prove that it's Lipschitz, and it does not satisfy any separating condition because 2 points here, I send 2 points here, which are much closer than they were here. And the closer, the higher. Well, okay. So I claim that F is not within bounded distance from any harmonic map, though F extends continuously to the boundary with value identity on the boundary. So this is a nice example. So before going into the proof is very elementary. If I cheat, it's elementary. Just an analogy. So the analogy that the analogy is that due to the mean value property, you cannot find a harmonic function from R to R, which is close to 2x when x is large negative and which is close to x when x is large positive. So this is the same stuff. So let's get to the proof or sketch of the proof. Why this example? Because it will be simple to tackle. And why? Because it has a lot of symmetries. So as you observe, F commutes to this symmetry and also to the parabolic subgroup that consists of translation along the real line. So by uniqueness, I remind you that the harmonic maps we end up with when they do exist that are within bounded distance from the quasi-symmetric map are unique. By uniqueness, if such a harmonic map existed, it would also commute to symmetry and to the parabolic subgroup. So it would have a spatial form. It would read as h of xy equal x some function of y. And why is it useful? It's because now the equation, the PDE that states that H is harmonic, reduces to an ordinary differential equation on Q, this one. And we can easily solve it. This is the whole family of solutions. Well, of course, we want the function to be 0 at 0 and infinity at infinity, so there is only one parameter solutions. And you easily check that none of them is okay. Okay? So what does this mean? It means that in our theorem, you cannot brutally remove the separation condition in the assumption that F is quasi-isometric. Nonetheless, you can weaken this separation condition. So the theorem, our second theorem, is a generalization of our first one. So the setting is the same. X and Y still are pinched Hadamard manifolds. And now F is a uniform embedding from X to Y. And the fact is that F is within bounded distance from a unique harmonic map. So what is a uniform embedding? So at this point, I have to admit that I totally blew it because I tried to use the same vocabulary as Pierre, and I failed. Usually I call this a coarse embedding, and I thought he would call it a uniform embedding, so I changed it, and no. So each time you see uniform, you read coarse, and it's the same thing as Pierre was telling you about in the previous lecture. So this coarse or uniform embedding, whatever you want, it's a map from X to Y for which the distance between the image is still bounded above by a linear function of the distance, but for which the bound from below is any unbounded non-decreasing function, which is allowed to grow as slowly as possible. Okay? So it's really weakening of the quasi-isometric assumption. Oops. Pardon. Okay. So it's easy to construct uniform embeddings or coarse embeddings that are not quasi-isometries. So for example, here, an embedding from H2 to H3, which is uniform and quasi-isometric. Then you select a geodesic in H2, and you associate to it a curve in a totally geodesic H2 in H3. This curve is parameterized with constant speed 1. And then you extend this map from H2 to H3. For the moment, it's only defined on the red geodesic by sending any geodesic that meets the red geodesic orthogonally to a geodesic on the right, which is orthogonal, which starts from the right point, and which is orthogonal to the horizontal, say, totally geodesic H2. So, of course, it's easy to find the map, well, the red map, so that you have a coarse embedding, which is not a quasi-isometric embedding, and you end up with a map from H2 to H3, which is a uniform or coarse embedding, but which is not quasi-isometric. Okay. So now what I want to do is give you a few ideas of how these theorems are proved without going into any nasty details, I hope. So I recall you that we start with a, say, quasi-isometric, to make things easier, map from x to y when x and y are both pinched Hadamard manifolds. And so this map F has a boundary value at infinity. Okay? And we want to find a map, harmonic map, which has the same boundary value. As I said, we want to solve a boundary value problem at infinity. Okay? We don't know how to do that. So instead, we will try to solve bounded boundary problem, bounded Dirichlet problem. But to do that, the first step is to replace F, which can be nasty. I mean, it might not even be continuous, given the upper bound condition. You know? We want to replace F with a smooth map. Oops. Okay. So this is the first step of our proof. There are only 4 steps. Don't worry too much. And we will replace F with twiddle F. That's how you say. And for point X in the source manifold, its image is defined at the center of mass, whatever this means, of the image of, say, the ball with center X and radius 1. So, with a reasonable definition of the center of mass, first of all, we will end up with twiddle F, which is bounded, which is smooth, which is smooth. And this map twiddle F stays within bounded distance from F, because F being quasi-isometric, then the image of the ball with radius 1 stays within a ball with fixed radius, say 2c, and we have negative curvature. The balls are convex, and any reasonable definition of the center of mass will send, will provide that the center of mass of the image of B of x1 will stay in this ball with radius 2c around f of x. And, if you do things correctly, actually you end up with a twiddle F that will replace F, and which is smooth now, and with bounded first and second covariant derivatives. So replacing F by the smoothed map, we may assume that our original quasi-isometric map is smooth with bounded first and second covariant derivative. So now, as I said, we want to solve bounded Dirichlet problem. So we fix once and for all an origin O in X. And for each ball, big ball, with center X and radius R, we will be able to solve the Dirichlet problem on this ball with boundary condition F. Recall that now F is assumed to be smooth. So this is a theorem by Schoen and Uhlenbeck that the corresponding bounded Dirichlet problem. So find a harmonic map defined on the closed ball, which is harmonic on the open ball and with boundary value F, has a unique solution and is smooth up to the boundary. So now we have this whole family of harmonic map HR, which are only defined on balls with bigger and bigger radii. And of course, what we hope is that these harmonic maps will converge to a harmonic map or subconverge when R goes to infinity to the harmonic map we're looking for. And we should be within this finite distance from F. Okay? And so the crucial step in our proof is to show that we have a uniform bound for the distance of F and HR on the ball with radius R. Uniform bound that does not depend on R. And now it's an easy step. It's a standard compactness argument. I will give some details on this step on the next slide. So now you want to conclude that the sequence or the family of maps HR converges or subconverges to a harmonic map. And since you have this uniform bound for the distances between F and the HRs, then the harmonic map, the limit harmonic map, will be within bounded distance M from F. And you are done. Okay? So, just a hint of how the compactness step works. Well, it relies on the so-called Chang's lemma. Well, the Chang's lemma is an analog in the realm of harmonic maps of the Schwarz lemma that Pierre told us about some minutes ago. And it states that when you have a harmonic map, well, don't pay attention to the assumption on the manifolds. If you have a control on the harmonic map, then you have a control on its derivative. And specifically, if it sends a ball to a ball, then you control the norm of the covariant derivative at the center with the radius, linearly with the radius of the ball that contains the image. And of course, the constant does not depend on the point. So this Chang lemma is a clever consequence of the Weissenbach formula and the maximum principle. Now, how do we use it? Well, since we have a uniform bound for the distance of the harmonic maps HR and F, and the map F is supposed to be Lipschitz, because now it's a smooth map, remember, smooth map with a bounded covariant derivative, then the Chang's lemma and the Ascoli theorem show that the HR converge or subconverge uniformly on compact subsets of X. But now the harmonic equation is an elliptic equation, so that elliptic regularity tells us that not only you have uniform convergence, but you have convergence in the C2 sense, and then the limit harmonic map is smooth and harmonic, and so on. Okay? So, now what I would like to do, rather than give details on the other steps of the proof, is to to give you, well, just what I wanted to say before is that, well, these 4 steps of the proof do work in the same fashion for either assumption that F is quasi-isometric or coarse embedding. It was the same. On the 3rd step, well, you have to, in a way, use the fact that F has boundary values. So this is already granted for when F is quasi-isometric, as I told you. And I want to explain you that in the case that F is not supposed to be quasi-isometric, but is a uniform or coarse embedding, then basically it still has boundary values. So, not everywhere, not in every direction. So precisely what we prove is that a uniform embedding between still our 2 pinched Hadamard manifolds does have boundary value outside a very small set of the boundary of X, especially outside the set of Hausdorff measure 0. So we actually use this result and rather a quantitative version of this result. So first, this is an example to show you that we cannot omit this restriction that we work outside the set of Hausdorff measure 0. So this should remind you of my construction of coarse embedding from H2 to H3. But here I use the right geodesic descent to a nasty-looking curve in the plane, which spirals away to infinity. And of course, the image of this geodesic, the red geodesic, doesn't have any limit direction. Okay. So, I will give you a hint of how to prove this previous result, but just to feel more secure, we will assume from now on that we work from H2 to H3, so constant curvature, low dimension. So just a notation, I will fix the point x0 in H2, its image is y0, and when psi is a unit tangent vector at the point x0, I will denote by psi t larger than 0, the corresponding geodesic ray. Okay? Shorthand notation for the geodesic ray. So, this is a quantitative version that leads to the theorem I just wrote on the previous slide that states that coarse embedding does have boundary values in many, many directions. So this is a quantitative version of that. This leads to a quantitative version of that. I wasn't very careful with the quantificators, of course, just a rough idea. So what we prove is that we're at the point x0, and for many directions, then the corresponding geodesic rays linearly goes to infinity, at least after a certain time. So this is what is written here, basically. You go away linearly with t, when t is large enough. And as a consequence, it is easy to see that for such a geodesic ray, the image has a limit direction when t goes to infinity. So the proof that the first statement implies the second is a standard hyperbolic geometry, because you have the point y0 here, and the other 2 vertices of the triangle are the images f of psi and f of psi n plus 1. They are far away from y0 when n is large, at distance at least alpha n. while the distance between these 2 points, since f is C Lipschitz, is less than t. I don't know what there is 2. Okay? So then the angle here is basically e to the minus alpha m. And what is nice, is that this is a convergent series. Okay? So the difference of the angles is a convergent series, so the angle converges. Okay? Now I will try to give you a hint of the proof of the first assertion. So we want to prove that for many, many directions in the unit sphere, the image of the corresponding geodesic ray goes linearly to infinity. Okay? So this will be a volume argument. So we first fix a time t. And we consider the ball with center y0 and radius alpha t. This is the place where you do not want to be at time t. You want to be outside of it. The good guys are those for which the image f of psi t is outside this ball. Well, we are on the hyperbolic plane, hyperbolic space, so this ball has volume e to the 2 alpha t. And so you can cover it, but this much balls with radius, say, 1. Now your map F is a coarse embedding. Yeah? So the separation condition yells that each pre-image of each of these balls with radius 1 is included in a ball with a fixed radius. And still you are in hyperbolic geometry. When you have a really big ball with radius t, then a ball with radius L intersects the sphere with radius t with an angle of the order of magnitude e to the minus t. And you have e to the 2 alpha t such cones. So that the volume, the bad volume, is not larger than e to the 2 alpha t times e to the minus t. And this is negative exponential when alpha is small enough. Now this is again a convergent series. So when capital N is large enough, this series, the tail of this series is small, less than epsilon. And this proves that for a set of measure greater than 1 minus epsilon in the unit sphere center that x naught, then for any integer n, the image of psi n is far away, as far away as you want, from I naught, the right distance. And you extrapolate for the non-integer value of t using, again, that f is a uniform embedding. So to sum up, you have that for a set of measure 1 minus epsilon, then of a direction, then the image of a corresponding geodesic ray goes linearly to infinity with speed at least alpha. Okay, and I will just end up by saying that the same type of volume argument proves that for a couple of unit tangent vector in a subset of almost full measure, then not only the images of the corresponding geodesic rays have limit directions, but they have distinct limit direction. You can quantitatively bound below the angles between the limit directions. So, okay, I think it's a good time to stop.
Thank you for your talk, and it is time for questions now. Anybody would like to ask a question? Can you please tell us where the assumption that you have a pinching condition on the curvature is? In which of the steps of the proof you use this assumption?
Actually, you didn't see it. This is true. Because I cheated, for example, here, it was my point when I said to simplify the matters, I would work from H2 to H3.
Yeah.
Because then I was able to cheat you. Here I am speaking freely of the measure on the sphere. But which measure am I speaking of? So when you are working in a homogeneous space, when you are working on H2, H3, well, it's a unique measure you can think of. It's a Riemannian measure, for example. But this would not do for our purpose if we are working in variable curvature, say. So then the measures we are speaking of here have to be the so-called harmonic measures. So perhaps okay. What is the harmonic measures? And you are in a manifold, Riemannian manifold. You fix a point, you have a ball. And then you can solve the Dirichlet problem for functions. You are given a continuous data at the boundary, and there is a unique harmonic function with this boundary value. Okay? And the value of this harmonic function at the center is associated by the Ries representation theorem to a measure on the sphere. Okay? This is the so-called harmonic measure at the center for the ball. Okay? And these are the measures we will be working with in general. And the point of the pinching assumption is that we have uniform estimates for pinch-Tadamar manifolds for the harmonic measures. So for any sphere, in my pinch-Tadamar manifold, I have a uniform control of the harmonic measure of a cone with angle theta. So a lower bound and an upper bound. The upper bound is states that these harmonic measures satisfy a uniform Franzmann condition with constants that do not depend neither on the center you're working with, nor on the radius. And, well, I pronounce the name Franzmann, so we'll see it's related with what I stated, that set of bad directions of Hausdorff dimension 0. I mean, it goes hand by hand. And so this is in particular here that the pinching assumption goes into the picture. And also in step 3, but it would, I would have to explain you about the step 3 to tell you when this goes into the picture. So it's difficult.
Step 3 is what?
Step 3, is when I prove that a uniform bound for the distances between F and the harmonic maps, solutions of the bound Dirichlet problems.
Thank you. Anybody has another question? Then let's thank the speaker again for this nice talk. Thank you very much.